Before we get started with the work that we're going to do in the next couple of series of videos, I thought it would be a good idea to talk about some matrix preliminaries. Suppose we have a matrix A, a 2 by 2 matrix, the top row of which is AB and the bottom row of which is CD. I'll interrupt myself right away and say some authors use square brackets to denote such a matrix, and the author that we're using is using parentheses. I'm fine with you using whatever you're comfortable with. Suppose we have a column vector x and it's got entries x and y. We can multiply a times x by writing a, b, c, d times x, y, and we multiply the entries of the row AB by the column xy pairwise and then add together the results. That's going to give us ax plus by. Multiplying the entries in the second row CD by those same entries xy is going to give us cx plus dy. Just to put some numerical context to this, suppose A is 3, 5, 4, 7, and I multiply that by the matrix X, which is, 2, 5. Then we have AX is equal to 3, 5, 4, 7 times 2, 5. And that's going to give us 3 times 2 is 6, 5 times 5 is 25. Add those together. Bottom row, 4 times 2 is 8. 5 times 7 is 35. Add those together. And we end up with the vector, the column vector, 31 and then 43. I really don't care what those numbers are. But what I wanted to point out was multiplying a matrix by a column results in a column, right? So a matrix times a vector is going to give us a vector. So if you know that A is a matrix and X is a vector, then when you see AX, you can know immediately that's a vector. Another important fact is that if we try to multiply X times A, then we have the column XY times the matrix ABCD. This product is actually not even defined. We would take the entries of the first matrix and pair by pair multiply them by what we get in the first column, but we don't have enough entries in the matrix XY. There's only one entry in the first row. I could multiply that by A, but I have nothing left to multiply by C. The point here is the order in which we multiply matrices matters. We don't get to write them in whatever order we want. Next thing I want to tell you about is something called the identity matrix. There is a 2 by 2 identity matrix. It is 1, 0, 0, 1. And there's a 3 by 3 identity matrix, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Yeah, there are a whole bunch more of them, different sizes. The 2 by 2 is sometimes denoted I2. The 3 by 3 is sometimes denoted I3. This matrix is special for a couple of reasons, one of which is that if I multiply the identity matrix by some matrix A, if A is the right size and is a square matrix, then it actually doesn't matter the order in which I write the product, A times I times A. They're both going to give me the original matrix that I started with A, and that's why this is called the identity matrix. For example, we can consider that A, B, C, D times 1, 0, 0, 1. We once again multiply the entries in the first row of the one on the left by the first column in the one on the right. A times 1 plus 0 times B is going to give me A. Doing the same thing with the entries of the first row on the left and the second column on the right, it's going to give me A times 0 plus B times 1. Continuing on, multiplying the entries in the bottom row on the left by the first column on the right is going to give us C times 1 plus D times 0. So that's going to give us C. And then the entries of the bottom row multiplied by the entries in the second column on the right is going to give us C times 0 plus D. And you'll see it works whether you write it as A times I or I times A. The result is the matrix that you started with. In the previous set of videos, we saw how we can represent a system of equations using a matrix, like an algebraic system of equations. And if we have here ax equals 0, now remember, the matrix times the vector gives a vector. So this is ax equals 0. Now this 0 is a vector. And again, depending on whether we've got 2 or 3 unknown functions that we're going to be working with in our systems, the 0 vector is either 0, 0 or 0, 0, 0. Yeah, there's a whole bunch of these too. Essentially, the 0 vector is just a column vector that has all the entries equal to 0. Yeah, it could be a row vector too, but we're not dealing with that. Back to this system, this ax equals 0 is a system of equations. A vector x that makes the system true is the solution to the system. And a result from linear algebra is that if ax equals 0 has a solution when x is not equal to the 0 vector, then the determinant of the coefficient matrix A is equal to 0. I'm going to unpack that just a little bit. If x is equal to 0, then A times x is equal to 0, and you get a solution to the system. X equals 0 is called the trivial solution. Saying that we want a solution where x is not equal to the 0 vector is saying that we want a non-trivial solution. And that'll happen if the determinant of A is equal to 0. If you have not taken linear algebra, don't worry about it. You just saw what we need to see from linear algebra. This takes like a month in a linear algebra class, and good news for you, we're just using the result. The last thing in this preliminary conversation is going to be augmented matrices, and actually a process called Gaussian elimination. And I'll say now that if what I tell you now is not sufficient, then that's what you want to look up, Gaussian elimination. Suppose we have a system 2x plus 2y is equal to 4, and 8x plus 3y is equal to 5. I know, not a very interesting system. Doesn't matter. This can be represented as an augmented matrix. The first row is 2, 2, 4. The second row is 8, 3, 5. And what I'm going to do is put a vertical line before the last column 4, 5, and then wrap everything else in parentheses. We saw before how we can represent a system using a matrix equation. This is another way to represent a system. This vertical line stands in place of the equal sign. If I wanted to solve this equation by elimination, maybe I identify the equations 1 and then 2. I might want to eliminate the x from the second equation, let's say. So what I might do is take equation 2 and subtract from it 4 times equation 1. Equation 2 is 8x plus 3y equals 5, and then 4 times equation 1 is negative 8x minus 8y is equal to negative 16. And adding those together gives us 0x, that's what we were after. And then negative 5y is equal to, what is that, negative 11. Okay. We can do all that same stuff with these rows of the augmented matrix because the rows of the augmented matrix exactly represent these equations. And the way I would write this is I'm going to replace row 2 using row 2 minus 4 times row 1. Row 2 is 8, 3, 5. Negative 4 times row 1 is negative 8, negative 16. And adding those together gives me 0, negative 5, negative 11. And then I can replace row 2 with the result of that giving me 2, 2, 4, 0, negative 5, negative 11. I have a new matrix that represents basically a reduced system. In the first case, our new system using this third equation that I'll call equation 3 is 2x plus 2y equals 4, and then negative 5y is equal to negative 11. You'll note you can use the second equation to find what y is, and then back substitute to find what x is. Doing this with an augmented matrix is exactly the same thing. In the case that I have something like 2x plus 3y is equal to 0, and then negative 4x minus 6y is also equal to 0, the augmented matrix is 2, 3, negative 4, negative 6, and then a vertical line. The columns or the last column is 0, 0. Doing a similar thing to what we did before, suppose I want to replace row 2 using row 2 plus 2 times row 1. Row 2 is negative 4, negative 6, 0, and then 2 times row 1 is 4, 6, 0. You probably already saw this coming. We get 0, 0, 0. So the augmented matrix becomes 2, 3, 0, 0, 0, 0. In other words, this collapses into one equation. Either of the original equations, 1 or 2, is the set of solutions to the system, or I should say any ordered pair satisfying either equation, is the solution to the system. And now let's consider the determinant 2, 3, negative 4, negative 6. Remember that to compute a determinant, we multiply the upper left by the lower right, and then subtract the product of the lower left times the upper right. In this case, that's going to be negative 12 minus a negative 12, and that gives us 0, aligning with what we said before. And when a determinant is equal to 0, an associated system has a solution other than the 0 vector, or in this case, other than xy is equal to 0, 0. I think we've seen enough preliminaries. Now we're going to put this stuff into context, and that context is solving systems of linear differential equations using matrices.